Looks like we're live. Hello everyone and welcome to yet another recreational programming session. How about that? Let's make a little bit of an announcement and officially start the stream. Maybe, I don't know. Let's give it a try. So, it's gonna be Red Circle live on Twitch. And what are we doing today on Twitch? Today we continue working on our programming language. Right, https://twitch.tv/tsoding, and I'm gonna ping everyone who's interested in being pinged. And there we go. It is what it is, and it isn't what it isn't. Is it not? I think it is. All right. So let me fetch the latest changes for the language. Right. So I think it's and merge origin master. Also, I think I need to rebootstrap my compiler, so let me quickly find the bootstrap instructions and quickly do them. Right, so after we compiled everything, we need to make the executable, right, give the permission for the executable. And after that, I'm gonna try to compile the compiler with itself. And the compiler managed to compile itself. That's actually pretty exciting. So now we have the executable. So this is the executable, almost 200 kilobytes. And it should be able to recompile itself, right? So it can recompile itself as many times as you want. All right, so what we're going to be doing today? Today we're going to be actually trying to attempt to make the type system of Porth a little bit better, right? So right now the type system of Porth is rather poor, right? So it consists of only 4 primitive types, only four primitive types. So the first type is an integer, and this type is basically represents the word of the machine you're running on, right? So it's just like a 64-bit number. There's nothing special about that. So another type is a Boolean, and it represents the Boolean logic value, and it is used for things like ifs and loops, right? So essentially ifs and loops, they expect the type to be Boolean for their conditions. And this is basically to separate the intents of like an integer that stores value and a Boolean that stores the value of conditional operations and stuff like that. Another type that we have is a pointer, and it's a pointer somewhere within the memory that points at some data, right? And that's very important, that it only points at the data. It doesn't point at the code. But the problem with that pointer is that it doesn't know what it points at. You need to know what you're pointing at, right? So, and essentially it kind of acts like a void star in C. If you ever programmed in C, you probably know what is a void star, right? So it's just like a general pointer that just points at something in the memory, and we don't know what it points at. And the fourth type is an address. It's almost like a pointer, but it doesn't point at the data. It points at the code. And through address, we can pass around pointers to functions. So it's essentially pointer to a function. You can call an address. You can't call a pointer, but you can call an address. And for the longest time, we had only these 4 types, right? So, and in fact, I re-implemented the whole compiler in itself using only these types. So it wasn't particularly convenient because quite often I need to pass a pointer to a huge structure, and the only thing I can use is a void star, right? So I can only use void star, and I don't really know what's actually behind that pointer, or there is like no compiler that will check that for me. And I think the time has come to actually change that. So today's stream is going to be dedicating to making pointers a little bit better. So essentially, on top of pointer being just a pointer and address in the memory, I wanted to actually store the information about what it's pointing at. Right. So since our type system only supports the primitive types, so far it's going to be pointing only at primitive types. Right. So instead of just having pointers, we will try to introduce pointers to integers, or pointers to booleans, or pointers to pointers, or pointers to address. Right, so basically, today we're gonna raise the level of kindness, right? Do you guys know what is a kind? Do you guys know what is a kind? Kind is essentially, you know, the type of a type, if that makes any sense. Yeah, like in Haskell. So essentially just a regular type, it has kind of a set, right? So if you have an integer, integer represents a set of numbers, right? It is basically a set of numbers, all of the, you know, integer numbers. Like float is yet another set, and so on and so forth. Right, so, and if you want to, for instance, express something more complex types, right, a pointer would be rather... So the problem with pointers, like in C, is that they're syntactically very, very noisy, so it's very difficult to see what they actually are. If the pointers in C looked like this, right, you would say that the pointer is a function that takes one type, an integer type, and returns another type, the pointer to an integer. In some sense, you can say that the pointer is a function that takes one type, one set, and returns another set. So the type of a type, usually in Haskell and other like similar function languages, is called kind. Right. So today we're going to introduce a new type that has a higher kind. Right. So today we're going to introduce pointers that are parameterized by other types. Right. So, and there is a lot of, like, for example, in Go, there is a lot of types that are parameterized by another types, right? So one of them is a pointer. Pointer is parameterized by another type. The channels are also parameterized by another type. The arrays are also parameterized by another type, and so on and so forth. So in a lot of languages, you can think about type system as sort of like its own language with its own values and its own functions, right? For instance, in C++, there might be like a type function array that actually accepts another type, right? And the size of the array, it accepts two arguments. You can think about array as a function that is executing at compile time, and it accepts one type and one value, right? So, and yeah, so basically we're going to introduce a new sort of function that accepts a type. So we've got some subs, so let me actually acknowledge them super quick. Okay, so Luke Lane resubbed for 2 months, I think. Thank you, saying hello. Robin the Bird Gamer, thank you so much for tier 1 subscription, your first subscription, by the way. Welcome to Epic Porth Club. Nichlete, I hope I pronounced your nickname correctly. Hi. Thank you so much for 2 months. Aaron and Kurnas 2000, let's go, new stream. How are you sodding? I'm doing fine. You know, keep developing my language. 41 UA or 4 Lua, I don't know how to pronounce that. Thank you so much for tier 1 subscription. And UC10, thank you so much for 5 months of tier 1 subscription. Thank you everyone. I hope I didn't miss anyone. All right, so how I'm going to be approaching all of that? So let me open the source code of the compiler. Maybe I'm going to actually open something like this. Okay, so as you can see here, we have some sort of a signature, right, for a procedure. So usually here we put all of the types that we accept, and here we put all of the types that we return. So I would like to, like, for this entire thing to work the following way, right? Imagine that you create a procedure, right? And in the inputs, you just put some types, right? Integer, Boolean, integer. And what you're effectively doing, you're pushing a type onto some sort of like a type stack, right? So imagine that here you're writing a program, but not using values, but rather types, right? And then you have a special function called a pointer, right? And what this function does, it takes the type on the top of the stack, right, and turns it into a pointer to that type. So you would consider like int pointer as a pointer to an integer, right? You see what I mean? It's basically, it's almost like with plus in a value context, right? In the value context, when you do 1, 2, you push 1, 2 onto the data stack, and then you do plus, and you do operation on the elements on the data stack. Here we have a type stack, and pointer could become an operation on the types on a type stack. Right, so... And the same thing is going to be here as well. Unfortunately, right now, pointer is not considered to be an operation. It is its own value. For the sake of backward compatibility, I think I'm going to leave the word pointer, the combination of characters PTR, as it is. It's still going to mean void star. But for the pointer to something, I'm going to introduce a separate word. Right, so I don't really know what's going to be that word, and I don't think it matters that much, but for now I'm going to use pointer to. Just a pointer is just a void star, but pointer to is type function that accepts a type on the top of the type stack and turns that type into a pointer to that value. Right, so, and you can actually apply it several times, right? So pointer to is actually several pointers, right? So basically it's a pointer to integer. And that also produces something like you can have a pointer to a pointer, but this is where this chain would stop, right? So it basically pointer to like void. And what's interesting is that you can also probably have a pointer to address, which also makes sense. So yeah, this is how I'm gonna go for now, right? 3-stack programming, yeah, this is a 3-stack programming. So yeah. I think that's basically it. Maybe in the future we're gonna also introduce something like array, right? And array is gonna be similar to C++, by the way. Maybe it's gonna accept a value and the size, right? Something like this. So this function accepts array of 5 elements, and this is the type. So maybe we will allow values in the type context, so you can construct an array of 5 elements. What's interesting is that multi-dimensional array is going to be very interesting. So what if we... Yeah, what if we actually say that the size of the array is going to be like the first thing, and then the type is going to be this thing? That way you could define something like 10, right? Then you have a row, and then you have the second array. So this turns into array of array. This is actually very interesting. Yeah. So this is a 2-dimensional array. Yeah, you can basically use the same reverse Polish notation to describe the types. Look at that. This is a multi-dimensional array 5 by 10, maybe 10 by 5 actually, because the row is this one, right? So this is its own separate type, which is the parameter for this type constructor. Yeah, that's actually very cool. That's very interesting. So you can have like basically its own type language, but of course none of that is implemented. It's just like I'm fantasizing about stuff. So yeah, but for now what we need to introduce just a regular pointer to, right? So this is going to be pointed to. So let me take a look at the possible subs. So thank you so much, Lil Baim. I hope I pronounced your nickname correctly. Thank you for tier 1 subscription. Okay, so let's take a look at the type representation that we currently have in a language. Currently, since we only support 4 primitive types, we just have a single number representing a type, right? So here's the types, and here's basically enumeration representing the types. So since we are going to introduce not only primitive types, but also pointer to types, what I want to do, I want to turn type into some sort of a structure, right? So it's going to be basically size of type, right? So it's going to be reset. And then we're going to have type, primitive, right? Which is going to be basically an integer, offset. Right, and the value of that primitive thingy is going to be just like one of these values. And then we're going to have type something like PTR count. Right, PTR count size of integer of set end. And basically what it means is how many times, how many layers of pointers you have over this primitive type. Does that make any sense? I think it does. Just a regular primitive type is just like integer, but with the pointer count equal to 0. And what's interesting is that the operation pointer2 could be just an operation that increments the pointer count for the type at the top of the type stack. Right, so essentially in the type you have like integer, and pointer2 takes whatever you have at the top of the type stack and just increments its pointer count. Not a bad idea, actually. I think it's actually a pretty cool idea. And maybe we're gonna have more properties of the types, and these type constructors are gonna be basically modifiers of these properties of the types. So pretty straightforward, actually. So it kind of like the whole thing like echoes in a type system. The concatenativeness of Porth echoes in its type system. The type system is also concatenative. Right, so the language itself is concatenative, and type system is also concatenative. It's its own concatenative language, separate concatenative language. I really like this idea. This is so cool. So there's so much freedom for intellectual masturbation in here. It's just insane. We're just ref counting type system of pointers. Yeah, basically, I guess. I don't know. So, but this is only for now, right? So it's just like a quick hack to introduce like more powerful pointers. So at least give some information to pointers to about what they're pointing to. In the future, maybe it's going to be slightly different. So we're just developing a basis for this entire thing. Right. So we're just developing a basis. Okay. So the problem is, throughout the code base, throughout the entire code base, a type was always considered just a single number, right? And now we are starting to treat the type as a structure. So, and since we don't have a very powerful type system, it's kind of difficult to refactor all of that. So, what I'm thinking is that we probably can introduce like a very quick hack to just get the typed pointer as quickly as possible. And once we get them, we can refactor that a little bit better in the future. So essentially, this number, this type number, specifically we store types only in two places, I think. In the constants and in the type stack. So if I take a look at the check, so there should be definition of a type stack somewhere. Maybe it's actually here. Type stack. So here is the type stack, and the type stack stores the current type, the location where the type was defined in the source code, and the previous type frame. And basically this entire thing forms a graph. So this is basically the, you know, some sort of like a stack-oriented graph, yeah, or stack. I don't know. Oh yes, somebody in the YouTube comment section actually said that I kind of reinvented a thing called graph structured stack, I think. Right, I never heard about this entire thing, but apparently I reinvented this thing with my type system. It's when you're using a graph to represent a stack. So you have a directly acyclic graph, DAG, and every path in that graph represents the state of some stack. I kind of reinvented that, but not really. So in my case, it is not really a graph. In my case, it's actually always a tree. I know that tree is a graph, but in my case, it is always guaranteed to be a tree. So in here, they're actually trying to compress even the tree into like a graph. In my case, compressing that into like specifically graph is not really neat. You can always keep it as a tree. So in my case, we have like a tree structured stack rather than graph structured stack. So yeah. It's actually really interesting. Like when I was thinking about the data structure for the type checking, I didn't even know. Like I guess that somebody probably had a similar idea, but I never knew the name of that idea. Okay, so I'm gonna put that in the description just in case if anyone is interested. So graph structured stack. All right, so, and yeah, so the type right now is an integer and it's kind of difficult to change that. So what I'm thinking is that I'm gonna basically turn this integer into a structure. Right, if you think about it, an integer is a 64-bit integer. It's actually a lot of memory, believe it or not, and we're using that memory to store 4 values. Something that can be stored in 2 bits, right? So we're wasting 62 bits, basically, right? We're wasting 62 bits per a type. So what I'm thinking is that I can just take 64-bit number and split it in half, right? So let's say the first 32 bits are the primitive type, and the second 32 bits are the pointer counter, right? And that way I don't really have to like change the memory layout or anything like that, and just like, you know, compress all of that into that single thing. And what's interesting is that we also have situations when, for instance, we are splitting on different types, right? For instance, in here, right? So we accepted the type, and we're just seeing, is that an integer? And in case of an integer, we do one thing, and so on and so forth. And when we reach something unreachable, it crashes. So essentially, if I convert the number into a structure, just a regular primitive type without being pointed by anything will act as usual. So all of the code that expects this number to be like a regular number, it will work. But as soon as it has one pointer count incremented, it will hit all of the unreachable paths in here. And this is where I will know that I need to go there and modify something. Does it make any sense? I'm not sure. So basically, it's a plan to keep backward compatibility with existing code. So existing code expects type to be just a number, and just a regular type without being a pointer still works as a number. But as soon as you turn it into a pointer, it will not work anymore, and it will hit all of the unreachable paths. And this is where we'll know that we have to go there and modify. I hope that makes sense. So yeah. So essentially, it's just like a plan to slowly migrate the code into a new state where implementing the type system becomes easier. I hope that makes sense. Droka87, thank you so much for your subscription. Thank you. Really appreciate that. And Legerati, thank you so much for Twitch Prime and Little Bime. I think I already acknowledged that, but thank you so much for a subscription. I love how the failure exit code used to either 1 or 69. So usually I reserve 69 specifically for unreachable. So I know from the exit code of the application that something that shouldn't happen has happened. Right, so usually 69, exit code 69 in my code means unreachable specifically. So Torrel Nor, thank you so much for Twitch Prime subscription. Thank you. So just a regular one is usually like an error, just a regular error, like for example compilation error. But 69 specifically is unreachable state. Okay, so let me see. I suppose we probably want to have some sort of like procedures that maybe spill the type onto a stack, right? So let's actually call it type, and the second one is going to be type, right? So this one is going to accept an integer, and of course both of them are going to be inlined, right? So these things are inlined, and this thing will return the pointer counter and the type, right? So the primitive type itself. So how are we going to be doing all of that? So this is supposed to be, as already said, a counter. Okay, so that means I need to take the value, so I'm gonna call it value x. And what I need to do with that value x, I need to shift it to the right by 32 bits, right? So shift right. And that's basically it. So if you look at that, let me actually see. So 64 bits. 64. All right, and I can query replace this entire stuff with, I don't know, dot with 0. So this is 64 characters. First 32 bits are gonna be the count, right? So this is the count, and the second one is gonna be the type. Even though we could probably allocate like 4 bits for the type, but I'm gonna keep 32. So and essentially I take the entire value in here and I shift it to the right by 32 bits and I just get the count. And for the second thing, right, what we need to do, we just need to remove this part from here. So that means we'll need to basically end it with a mask, right? And the mask has to be, you know, 32 ones, right? So luckily we have hexadecimal literal, so we can do things like 1, 2, 3, 4, 1, 2, 3, 4, right? There we go. So this is a mask. That will actually do all of that for us. Okay. Oh yeah, by the way, the number literal actually support underscores, and basically any underscore within the number literal is going to be simply ignored, right? So you can basically split like by 4 Fs and make it a little bit more readable. So, and that works with any number literal. You can actually do a binary one, right? So you can have binary literals that look like this: 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4, and then like sort of how many of these things, right? So 16 of them you can split by 2 or something like that, and that is still considered a number literal. I can even show you. So I can just like go to somewhere like main.porth, because that's how it usually is in all of the modern languages. So why not? I think it is very, very convenient. So it's going to be porth, compile, main.porth, and of course it compiled and you can run it, so it basically equal to 3255, right, essentially. It is essentially equal to that, so it is still a number, but as far as I know, like if you put a in here, it is not interpreted as a number anymore, which is kind of error prone, right? So it's super easy to confuse like a number and not a number, so maybe if it has a prefix, I'm gonna disallow this thing to be interpreted as a word. I haven't decided yet, so the language is not finished, so all of that is just bike shading. At this point, okay, so here I can just take the type and separate it into the counter and the primitive type, right? So, and then here I can collect both of these things back into the original thing, right? So essentially here I unpack the type and here we pack the type. Right. Here we pack the type. So how are we going to be doing all of that? So here we have a PTR count, and here we have a primitive, right? So PTR count. What about PTR count? So I suppose. I'll need to shift that to the left by 32, and then maybe OR it with the primitive thingy, right? So just OR it with primitive. But I'm not sure. Before I can do all of that, maybe it would make sense to end both of those things with the mask. Essentially just clean everything up, right? Just only use the lower 32 bits. Right, so and then we shift this thing to the left, and then we just OR it with the original one. So I think that's fine, right? So we can have something like that. Okay, so let me recompile the compiler just to see if it still compiles and stuff like that, and everything seems to be okie dokie karaoke. Okay, that's very cool. And the compiler can recompile itself, as you can see, so everything's fine. So now we can try to introduce the pointer to operation within the type context, right? So we need to see where it is defined. So let me find something like parse. I think it has something to do with contract. Yeah, parse proc contract list. right? So this is where we have this entire thing. This is a very old code. Oh my god. This is a very old code. Okay, so bike shader. Okay, cool. So we iterate through all of the tokens, right, of the Lexa, right? We iterate through all of the tokens, and then we take the token. If the token is a word, we try to parse that token as the data type, right? As the data type. And if it is equal to data type, we're trying to just push that data type onto the type stack. That's basically it. So what I'm thinking in here, what we need to do, we need to just like add another condition saying if you encounter pointer 2, just modify whatever you have on top of the stack. We might as well actually just do something like this. Right, so let's go to main.porth. And in here, we're going to have a foo, right, and in here, let's actually do integer pointer 2, right? So here we're supposed to do that. Integer pointer 2. It looks a little bit ugly, but again, it's just a syntactical thing, right? All of that can be, you know, fixed up a little bit later, right? I don't really care about specific names. Specific names don't matter right now. Okay, so as you can see, unknown type pointer 2 in procedure definition, right? So, and the first thing we probably want to do, right, is to add this condition in here, right? Dupe str, so this is going to be else. Dupe str and pointer 2 str equal, right? Str equal. Though, okay, so this one is interesting because we are dropping whatever we've got from data type when it was not successful. So probably we'll have to drop it in here. And maybe we don't have to drop it in here. Again, it's a very old code, so it was written before we even had any like LED bindings or peak bindings or anything like that, so it's a little bit painful to work with. Maybe I should spend some time actually refactoring this code, turning it into like sort of letify, if you know what I mean. Right. So I think that sounds like a pretty good idea. Let's actually try to letify this code. Right, so... It's actually a pretty common thing that I do on like during the development of this language. I letify some of the code, some of the old code. So if I take a look at the history, yeah, letify. Yeah, letify. Yeah. Letify. So, and I usually do that before like implementing the feature on a particular piece of code, right? So I just try to make that code a little bit more readable. Okay, so let me do a separate branch. So this is going to be pointer 2. And let's commit whatever we have. Implement type packing unpacking, right? Type packing unpacking. So Legerati, thank you so much for Twitch Prime subscription. Torlenor, thank you for how much for Twitch Prime, and Drake Zorn, thank you so much for tier 1 subscription. So I'm using Twitch itself for like a feed of subscriptions, and unfortunately Twitch doesn't have a feature that let me mark already acknowledged subscriptions. And so if I repeat somebody's name several times, I'm really sorry about that. But maybe that's exactly what you want, I don't know. So I used to use Streamlabs, but unfortunately Streamlabs just consumes too much resources for just a list of subscriptions, so I decided not to do that. Okay. So let's try to letify this entire thing. So what do we have in here? We have Alexa. So first it's a stack, but when we refer to a stack, do we pass it by a pointer? I think yes. So we actually refer to the stack by a pointer. So that means in here I can just do, okay, just a second. Let Alexa stack. Right, and I don't need these two things anymore, right? I just don't need them. So here I probably need this kind of stuff. And let's go to the end in here, right? So, and let's just go back to let, and like that. And within this code, everything that we're referring to, with Alexa at PTR, right? Query replace Alexa at PTR. We can replace it with just Alexa. Right? Wasn't that much stuff, but I mean that's fine. Then query replace stack at PTR. Replace it with just a stack, and okay. So that wasn't that much, which is rather interesting, but okay. So I guess that is that is basically it. So actually there's not that much to latify in here as far as I can tell, except maybe I do a lot of referring to token fields, right? I quite often do token type, token value, and I do all of this like pointer arithmetic. Maybe it would make sense for me to just like, you know, pre-allocate all of these things, right? To do something like token type pointer plus, and here I will just have type, right? So, and I can just like take this entire thing, query replace token type pointer plus with just a type, and make that stuff a little bit more concise, if you know what I mean. So in here, so this is just a type. So then we can have a value, right? So this is a value. Query replace token value pointer plus with just a value. So this is just a value. Maybe also location. Location seems to be used a couple of times. Actually, it seems to be used a lot of times, so it does make sense to do it like that. Query replace token location pointer plus, replace it with just location of our nation. All right. Did that make code a little bit more easier to read? Probably not, but that's fine. So let's align regular expression input. Okay. Seems to be fine. Right. So did it make it concise? Probably. One of the things we can utilize in here is probably the early return, right? So for instance, here we keep track of the bike shader, whether we return bike shader, and as soon as we encounter bike shader, as you can see, we just like set it to true and break out and just return like that. So I don't know. So far so good. I think this is okay latification of the code so far, at least. So I'm gonna just keep it as it is. So unknown word lock. Oh, this is because it's supposed to actually put it here. Okay. So, and the thing still recompiles itself, as far as I can tell. It still recompiled itself, and we can just run some tests to see if the tests are not broken. Just to see if the tests are not broken. Okay, it wasn't that much latification, but yeah, it is what it is. So parse proc contract list. So let's say latify parse proc contract list, and I'm gonna push that right into the repo. Just to save all of that, and let's move on like actual thing. Right, so here I try to do, try to parse the data types, and then the second thing I can try to do is, this one, I could have just used value, like so, and got rid of the drop in here. Okay, so this is just a value, this returns true, and then I'm gonna realign input There we go. If I try to recompile this thing, not enough arguments for dupe. This is because we're supposed to do a value. Okay, that's cool. Anything else? Not enough arguments for the swap. This is very interesting. Okay, so I'm actually simplifying the code, I think. Okay, so the code actually simplified. That's nice. All right, cool. So here I can just do value, right? And then I can do value at str, and is it equal to pointer 2, right? Str equal, and if it is, I'm gonna just do something like to do pointer 2 is not implemented yet, right? So let's actually say something like this, and of course here we might try to do true. Continue. Cool. So unhandled data on the stack, it's an integer. Yeah, I suppose maybe drop has to happen somewhere here, I suppose. Yeah, that makes sense. Okay, cool. The checker actually code this stuff. Okay, so if I try to now use my compiler on this example, right, main.porth. So I probably have to go here, main.porth. It will say pointer 2 is not implemented yet, though it would be also nice to know the location. So let's actually say located here. Right, and let's try to run it here. Pointer 2 is not implemented yet, and located it in here. Okay, so as you can see, we caught a moment where the user provided pointer 2, right? And we now just need to implement that, right? So we just need to go in here and do something. So first of all, we need to see if there is anything on top of the type stack, right? So pointer 2 requires something on top of the type stack, and if there is nothing on top of the type stack, we should throw an error. So we're basically checking the types for the type signature, right? So here we're not checking the types, we're checking the kinds, right? So we're checking the kinds. That's very cool, actually. So because pointer 2 is a type function that accepts types as arguments, right? And if it doesn't have enough arguments, you need to throw not really a type error, you need to throw a kind error, right? So it's kind of interesting. Anyway, all of these are very blurry category, right? So they're very blurry category. What is type, what is kind, what is value, nobody knows. So let me see actually. How do we know the size of the type stack? If I remember correctly, so it's somewhere in the types. Stack. Type stack, yeah, we can check if it's empty or not, right? So if the stack is empty, we should throw an error. So what we're gonna do in here, so I'm gonna do eput lock, right? And here we have an error. Not enough arguments for type constructor. Eputs, and so what is going to be the type constructor? I think we can just do value at str eputs. Expected 1, but got 0. So right now I'm hard coding the specific values because like I don't have a more general mechanism of checking the kinds of the type constructor, so I'm gonna just leave everything as it is, and then later I'm gonna make it less hard coded. All right, so it's gonna be eput, and then I'm gonna exit with this sort of thing, right? So let me try to run this entire thing, and as you can see, it does not complain, but this is because it does have a parameter, right? If I remove this thing, it should complain now. Not enough arguments for the type constructor pointer 2, expected 1, but got 0. So as you can see, we're already checking if pointer 2 has enough arguments, right? So we're already checking that, which is kind of cool, right? So what we need to do now, we need to take the top of the stack, right? So we need to take the top of the stack. Oh boy, so stack type stack top pointer plus, right? And then I just have to read that, I suppose, right? And it will give me pointer to the type frame, right? So this is what I have to do. So this is a pointer to type frame. So in the type frame, I have to take the type pointer plus, and then I need to read it as a value. So after that, I can spill that value onto the data stack, and there you go. Here I have the pointer count and the primitive value. Right, so what we can do in here is essentially I want to just increment the pointer count, but don't touch the primitive type. Right, so this is basically how I transform this type. And I suppose now I want to save it back into the type. Alright, so this one is rather interesting. So maybe it would make sense for me to put a type in here, right? So this is the type. So, and I read that type, right? I just basically read that type and I spill it like that. Right, I spill it like that. Then I pack it back, right? I pack it back and then I save it like this. So probably this sort of name, these two sort of names are not really great. So let's do something like unpack type and then pack type. Right, so we can pack and unpack it, so it becomes a little bit more symmetric. So I take the type value, I unpack it, I transform it, I pack it back, and I save it back into the same field in here. So I think I already had like type. So yeah, type here is a type of the token, but type here is the type on the type stack. So I'm not sure if this is a good idea generally, but they should properly overshadow each other, so that should be fine. In any case, so let's go to the types and let me find this thing. So this is basically unpack the type, right, and this one is pack the type, right, unpacking and packing. Cool, so that should be enough. So let me see what's going on. Cool. So it actually fell through. So that means all of this stuff worked correctly. All of this stuff worked correctly. So we can try to remove this to do. And now we have a pointer to data constructor or type constructor, right? Which accepts the type as a parameter. And what it does, it just increments the pointer count on of the type on top of the type stack, right? So that's what it's supposed to do, right? So, and it will probably bring a lot of errors to the rest of the code, because the rest of the code does not expect, you know, the types of these things to have like a pointer count, right, that is incremented by 1 and whatnot. So, and this is precisely what we want to see. Okay, unknown word. Okay, so it already complains about this kind of stuff. So let's actually remove this thing, and it should crash. There we go. So look at that. Look at that. It said that you have unhandled data on the stack. Then it tried to print the data, the type of the data on the stack, and it failed while trying to print that data. And it failed at types 98. It reached the unreachable. Right, again, because we only ever expected 4 types, we never expected to reach here. And the only way you can reach here is you have a pointer count incremented. So now it's completely like a different thing. So essentially, like, there is a huge value in handling the unreachable paths of the execution, because this handling of unreachable paths of the execution will help you to refactor your code in the future when the requirements change. You see what I mean? So it was unreachable because of the current requirements. The requirements have changed, and now this code became reachable, and you better know when your execution reaches the unreachable parts, when you change the requirements. This is a very valuable lesson right in front of you. Okay, I hope everything's clear. So let's actually try to handle these things. So what we're doing here, we're basically printing the type. So, and interestingly enough, I think we should not use data type to print this thing. I think this function should be called something like type as str maybe, right? So maybe display type, right? It will get the packed type. It gets the packed type, and it should basically turn it into a string for you to print somewhere, right? Interestingly enough, now this entire thing becomes rather complicated, and I suppose we can't just return hard-coded types anymore. We can't just do that. What we need to do, we need to probably use a temporary buffer to allocate the strings, right? So, all right, let me take the type and unpack the type, right? So unpacking the type, and I'm gonna bind it to count ptr. So this is a count ptr and the primitive, right? So in here, I think I'm gonna put the end of the temporary buffer, right? So this is the end of the temporary buffer. And this is where I'm gonna start appending things. So first thing I probably wanna append, I wanna append the name of the primitive types, right? So maybe I'm gonna even just take this entire thing. I'm just taking this entire thing. And, you know, just putting it like that. So, and now I'm gonna rename this to primitive. Not prime, but rather primitive. And so I'm also dropping something in here, and I'm not really sure what exactly I'm dropping, so I didn't think I need to drop anything. Might as well also do something like tmp append pointer, right? tmp append pointer, and I think it also needs to drop. I think tmp append returns the value, returns the pointer. So, and in here we don't need to return anything, we just like say that this thing is unreachable. Okay, so we appended this stuff, and now what we want to do, we want to iterate this amount of times. While dupe is greater than 0, we're going to be appending space pointer 2 to the buffer, right? We just keep appending that, and we keep decrementing that value. Right, so after that, after we constructed the entire thing, I think we need to just duplicate the pointer to the beginning of the buffer, right? Then I'm going to append the end of the buffer. Then I'm gonna swap this entire thing and subtract it, which will give me the size of the buffer. Actually pointer diff, it has to be pointer diff, and I'm gonna swap it again, and it will give me basically the string. So at the end in here, I should have the type integer pointer, hopefully. Unknown, oh yeah, we don't have that stuff anymore. Okay, so let me see. What was it called? How did I rename the procedure? I forgot how I renamed my procedure. So it's now called display type. So this should be called display type. Right. So, and we'll probably have to do that in all of the places where we were referring to data type. Right. Display type, unknown, wait a second. Const type, display type. Anything else? Display type. Display type. Okay, So pointer diff expects pointer but got an integer, which is rather weird. So let me take a look at the top of the stack in here. So what's the top of the stack? So we have an integer, which is, okay, so I forgot to drop this entire thing. Thank you so much. Right, so I just have a pointer, so this entire math should work out. So I put another pointer in here, so there will be double pointer. Not sure why there is 3 of them. Right, so there's a 1, there's another. Oh yeah, okay, so that makes sense. So now after that, we should have a pointer and an integer, which is exactly what we expect in here. Okay, so if I remove this entire thing, that should be fine. Okay, we've got something. That is very cool, isn't it? Yes. So we've got some sort of error. Very, very, very cool. Not really sure what exactly is the problem. What exactly is the problem? So it's reading from a where maybe I should have not like. Okay, so I have the beginning in here. What I did, I duplicated the beginning, right? I duplicated the beginning, I put the end, then I swapped it, and then I subtracted them, right? Expecting them to yield at least the size of the buffer, right? So that gives me the size of the buffer, and then I just do that. The only reason why I think it may not work out is pointer div doesn't work properly, or something like that. Though I can also try to do print just to see what's going to be the size of the entire thing. And I can clearly see that something did not work out in here, right? So something definitely didn't work out in here. This is not the size that I would expect, right? So this is too huge. So maybe I should not swap this thing, right? So maybe that's what I need to do. Yeah, that's really weird. Okay, so probably want to make a small break, make a cup of tea. And after a small break, I'm gonna try to tackle this bug yet again, because that's kind of weird bug. Not gonna lie, don't see any problems in here, though. This is annoying. Why is it so huge? I'm probably missing something. But anyway, let's actually make a small break and okay. So let me try to debug this entire thing. Right. So the only reason why this kind of stuff may happen, I think, if the count pointer and prim are not correct. So let's actually try to I don't know, print them. So it's gonna be puts, and we're gonna have something like count ptr print and prim. So let's actually try to run this kind of stuff. Okay, so count pointer is 1 and primitive is 1. Okay, that makes a lot of sense. I do agree with all of that. So in here, let's give it a try. So if I do, so here I supposed to have a pointer, right? Do I have a pointer? So we stop, and the type is, ooh, huh. Well, that's rather complicated. So I should probably use the Bootstrap compiler. Yeah, let's use the Bootstrap compiler to do this entire stuff, so it does not interfere. So this is the pointer, and everything seems to be fine. So one of the things I probably want to do, I know that it's supposed to be in the integer, so I can do 3 swap and then eputs, and I just want to see if it's going to you know, work more or less properly. Yeah, so that's what I'm talking about. we appended some stuff. But it just doesn't work. So TMP end doesn't seem to be pointing at where it's supposed to point, and it's so weird. Did it not point, did it not append what it's supposed to append? I'm really confused. Right, so if, for instance, I explicitly, so I'm gonna remove all of that, append, I don't know, QWE, TMP append pointer, and then I drop this entire thing. It should actually print that, but it doesn't. And I'm not sure what the hell is going on. So there's something really weird happening, and let me see. So I'm gonna do foo.porth. Right. So TMP end. This is where the this thing ends. Then I'm gonna do hello TMP append ptr. Right. Then I know that there is a 5 characters in here. I do 5 swap and then puts, and I would expect this entire thing to print hello, and it just should. There is no other like, you know, option in here. If it doesn't, there's something really weird going on. There's some sort of a bug happening. So let me see. Foo.porth, and something is not working. So puts expects a pointer. So might as well actually put 5 somewhere here. So, and this is also has to be dropped. Yeah. This is bad. This is straight up bad. Why this doesn't work? Let's take a look. So proc TMP append. So I'm just allocating that stuff. It's not append pointer. It's just append. It has to be just append. But why the type checker didn't complain about that one then? Okay, we have a very, oh my god, I know why. Okay, so we have think. So here's the 5, here is this thing, right? So, and then if I have a append pointer, after that, what do I have on top? Oh my god, this is so bad. Right, so it would consume that, and the drop would drop the rest of the thing. So it would drop the integer, right? It will drop the integer. So, and then you have this. Okay, I see. So this is, I just confused 2 different functions. So append pointer appends rather the pointer. Okay, so it is so bad actually. But I mean, it's not a bug, right? So append takes integer a pointer. TMP append pointer gets just the pointer, right? Okay, I shoot myself in the leg, but that's what you get for a weak type system. But we are in the middle of making the type system better, so I think we could be forgiven for that. So in here, we're gonna just do that, and I want to double check whether we return a pointer. Yeah, we do return a pointer here, and that's why we have to drop it. Okay, so that should be fine. So TP append and blah blah blah. So this one is just that. We keep appending this entire thing, then we take a difference, and so on and so forth. So this should work fine, hopefully now. So now let me try to run this entire thing, right? And unhandle type on the stack, and we have actually nothing in here, right? So this is already interesting, right? At least it doesn't print the garbage, right? At least it doesn't print the garbage. So I need to go back to the function where we had this kind of stuff. Unpack. I forgot the module where this function was. So it's called like this. Okay. So, and because of that I have to actually swap this entire thing. So I duplicate the begin, then I put the end, I swap them around, then I do pointer diff and I swap them again and I get the correct thing. So now, look at that. Look at that. Unhandled data on the stack, unhandled data on the stack, int pointer. Right. So, and the only thing for now, we can just like do drop and it works. Right. So that's actually very, very cool. So our type system is capable of recognizing like a pointer to an integer, which is kind of cool, isn't it? I think it's kind of cool. Right. We can't do anything with that thing yet, but we already have like this kind of pointer. Now we can do pointer to pointer, so we can actually do that several times. And as you can see, we have unhandled data on the stack, integer pointer to pointer to pointer. Pointer to pointer to pointer. So what else can we do with this kind of stuff? It would be nice to have some sort of an intrinsic that accepts sort of like any pointer type and sort of like unwraps it, right? To some extent. Essentially, it would be nice to have at, right? And if at, we can even do something like this. So I'm going to write in pseudocode. So it accepts a pointer to, right? And it returns a. So essentially, it dereferences this entire thing. It would be nice to have an intrinsic that looks like this, right? So it dereferences the pointer and it sort of like unwraps the pointer, and yeah, that way you can probably read from that thing. The question is how we're gonna implement that. Since for now, this one is rather interesting actually. Since for now, all of the types we can refer to, right? All of these types that are, let me see, integer, boolean, pointer, address, all of these types are 64-bit types. So that means these special intrinsics can always be translated into load 64, at least for now. Right, then later when we introduce smaller types, for instance U8, loading from that type would probably translate to load 8. So, yeah. The question is... So I'm just thinking how we're gonna approach that. I think I'm gonna just go ahead and introduce a new intrinsic, like straight up new intrinsic, which is just like a overloaded load. And on the type level, on the level of the types, right, on the level of the types, it's going to just unwrap the inner type of pointer to, basically decrement its pointer to. And on the level of a code generation, it's gonna act like a load 64. And that's basically it, I think. At least for now. Right. So yeah, let's go ahead and do that. So before I can do that, I think I'm gonna just go and commit whatever we have. Right, so this one is gonna be data type name. I think this is what it's called. Display type, and I'm gonna push that right into the repo. Okay, so let's go to the compiler, right? Let's go to the compiler and introduce a new intrinsic. So we already have intrinsics like load 8, load 16, load 32, load 64. We are about to introduce like overloaded load, right? So it's going to be const intrinsic just load, right? It's just like a load. Maybe I'm gonna be a little bit more specific. Load pointer to. I think that's a bit better, right? It's a load pointer to, and we'll see how it goes. Okay, so let's just go, and that's gonna be interesting. So 46, right? So this one becomes 47, and so load intrinsic load pointer to, right? And it's gonna be just at, right? It's just gonna be regular at. And by the way, here we probably should not put any spaces. Okay, so the other way around, where is the load? So else name at str at, right, str eq intrinsic load. All right. Okay, unknown load pointer to. That's what we should have. All right, when we encounter this thing, so this is basically type checking. Okay. Oh boy, oh boy, oh boy. So we have a type check load operator, and type check load operator just accepts a pointer and returns like an integer. So we'll have to have our special type checker for this thing, right? So we need to have a special type checker. Intrinsic. All right, so people are bike shedding yet again in the chat, nothing interesting. Pointer to, so it's gonna be token stack type check load pointer to, right? Type check load pointer to, though I might go to the definition of this thing, right? Type check load pointer to. So here we accept the token, right? Here we accept the token. Here we accept the stack. Here we accept the stack. Cool. So in the inputs, should be relatively straightforward. And then I take over for the token. So I could probably like copy paste this entire code, right? Because it's roughly what I expect here anyway. So this is a load and we expect a pointer. This one is rough because we expect, we could say that we are expecting a pointer, but this one is really interesting. It's kind of difficult to express that thing in the current type system for whatever reason. Maybe we should use expect arity. This is one of the things we can use. We can try to expect arity, and specifically we're expecting one thing, right? And then we can specifically check whether it's a pointer or not. And if it's a pointer, we're going to construct ins and outs accordingly. Yeah, I think that's going to be roughly what I want to have. That's going to be roughly what I want to have. Load the pointer. So clip 12, thank you so much for Twitch Prime subscription. Thank you. Really appreciate that. All right, so this is what I want to do. So expect arity. Let me try to do that. So I get that, and the arity is going to be actually 1, and that should give me the input stack, right? So that's going to be the input stack. So because of that, we don't really need this thing. So it's going to be just that. So I need to see how else do we use the ins and outs. Yeah, arity in this particular case just becomes ins. So maybe it doesn't matter. Outs, expect arity, size of type stack, tmp alloc. So we have token stack, original stack, then we have ins and we have outs. Right, and this is where we want to check the ins. Right, so expect arity guarantees that ins are going to have at least something on top of the stack. So because of that, I can do type stack top pointer plus. Then I can read this entire thing. Then I can take type frame type, right? Type frame type pointer plus. And I can probably read it, so I might as well actually bind it to here, right? So I'm binding it to here. And this one is interesting, so maybe I'm gonna also unpack the type. So in here I'm gonna have count pointer and the type. So, and this is very interesting thing. So if the count pointer is not greater than 0, right? So if it's not greater than 0, this is a straight up an error, like some sort of a type error. But I'm not quite sure how to report it properly. So I'm putting a hack in here, right? I'm putting a hack in here. So, and what kind of hack can I put? So I probably need to also take the location of that type frame. SKPL, thank you so much for tier 1 subscription. Thank you, really appreciate it. Okay, so this is the frame, and I might as well actually put it like this. So this is the frame, because I'll need like more information about the frame. Right, and within the frame I do type frame type, right? Pointer plus. Because of that, since I just need like more extra information, might as well just do dupe type frame type pointer plus. This is annoying because I also want to simultaneously split this thing. Okay, let's actually just go with the frame then. Okay, I also want to simultaneously split, and it doesn't allow me. Okay, frame type frame top pointer plus. No, not top type, right? And then I just read it as it is. Then frame type frame location pointer plus, and that's the location. And this is where I can probably split this entire thing. I can unpack the types, and here we're gonna have the count pointer, primitive type, and location that I can use for reporting. Finally, hopefully, we'll see. So, and if the count pointer is not at least like 1, we should say something like input lock error at can can only accept pointer to types. Yeah. So it's for now, right? It's only for now. But in the future, I think we're gonna have more general mechanism of detecting this kind of stuff. So before we only type checked primitive types. We never type checked more complicated types that are parameterized by other types, and that's why type checking mechanism like can't really comprehend that properly, and that's why I have to do this kind of stuff explicitly. So maybe by writing this code, by actually figuring out what's needed, I can come up with more general mechanism of type checking. So it's quite important. Okay, so now we know for sure that count pointer is, you know, is fine. So now I can try to construct the output type. And the output type is basically going to be count ptr 1 minus, then the primitive types, and I pack it back into the original type. So this is the type. So then I can just use the location where it was introduced. I think I can just like straight up use this location and type stack push. I think this is how I can do that. Right, so but I also have to provide the outs in here. Okay, so this is a new type, this is location, this is where I put this entire thing, and I just prepared the output type. Cool. So that's pretty cool. So this is the preparation of the output. After that, I can just go ahead and type check this stack. Hopefully I can type check the stack. So let me see if this entire thing compiles. Exhaustive. Okay, cool. So now we have. I essentially intrinsic load pointer. Yeah. So we're done with the type checking here. So the type checking is done for now, and now we're doing code generation. We are doing the code generation. Intrinsic load 64, right? And it's gonna be the same as this, right? So they're literally the same, right? Because you cannot point to anything but 64 bits for now. Right, so because of that, this should be fine. So, okay, anything else? All right, and handle data on the stack, cool. So now, look, it should be possible to return an integer, right? And that will not work, right? So it will say unexpected data on the stack, unexpected data pointer to an integer, right? So here is the pointer to an integer, but expected data is integer. So theoretically now I should be able to just say at, right? And it should type check. The entire thing type checks. Okay, that's cool. So there's no way to construct such type yet. There is no any way to construct such type, but you can accept that type and you can transform it back into its integer. So if you accept like something like boolean, like if you return something like boolean, it will not type check. Yeah, unexpected type integer, but the expected boolean. As you can see, it just took int pointer 2 and it unwrapped it, turned into an integer. But if I turn it into like boolean, right, if I turn it into a boolean, it will type check properly. So you can try to call foo, but you won't be able to call foo because you can't construct such type. Not enough arguments provided by foo. Right, so if you try to provide like 69, it will just not work. You can't construct such type. Right, as you can see, argument 0 is expected to be pointed to boolean, but got integer. So the question is, how can we construct such types? Right. So we already have mechanisms for memories, right? So we already have such things as memory. You can allocate a little bit of memory, and usually we just provide the size of the memory that we want to allocate, right? So I don't like this memory construction. I really don't like it, and initially when I studied the language, I didn't even want to introduce that. But I did it anyway because I needed something. I needed some way to define a chunk of memory. What I needed instead, I wanted to have variables, right? So I want to introduce a construction called var, right? And var is going to be almost like a memory, right? It's almost like a memory, but instead of providing the size as a number, you would provide a type. Right, so envar is supposed to be a keyword that is highlighted, but I wanted something like this. Right. So, and here's an interesting thing. When you push a memory onto the stack, this thing has a type of the pointer. Right, so when you use access, it's a pointer. But now we have a variable and we know its type. And essentially what I want to have, when I push type x, value x, it actually pushes a pointer to the value it holds. Right. So, and that's going to be the way you can construct such type. And then you can, for instance, read the value, right? And because of the type system, it will be type checked properly. Or you will be able to write something into that value by using something like exclamation mark, right? So that's what we need to implement next after we introduced the typed pointer. We need to introduce variables, basically like memory regions, but their sizes are defined not by specific numbers. Their sizes are defined by types. Does that make sense? Right. And at, of course, is going to be similar to, and exclamation mark is going to be similar to at, right? So it's going to be something like at, and it would accept the, like some sort of a value, a, and then a pointer to that value, right? Some sort of a pointer to that value, and it's not going to return anything, right? Thank you so much, Tito Ante. I hope I'm pronouncing them correctly. For Twitch Prime subscription. Thank you, thank you, thank you. Does anyone have any questions on what we're doing right now? Any relevant questions about like what's going on the screen? Like on topic questions, strictly on topic. Does anyone have any of those questions, please? Okay, so I'm not sure if I have enough time to introduce the variables, but I can try to. Right. We can actually try to do that. Will there be a way to have array variables like that? Yes, there will be also a way to have arrays. It's going to be the next step. This is a very good question, by the way, and we're going to have a special syntax of accessing arrays and stuff like that. But I'm not sure how exactly arrays are going to go. We'll see, we'll see. Planning to remove memory after var is working? Yeah, it is the plan. It is the plan to completely get rid of the memory, but you never know. Maybe memory is going to be a very useful mechanism by itself for something like a really low level. But I mean, you can just have an array of bytes, right? So if we're gonna have like a powerful enough type system that can have like a byte-sized types and arrays, you can just like define an array of bytes, and there you go. Here is your memory, right? Here is your untyped memory. So I don't know. I think we're gonna get rid of memory at some point. That's for sure. Will all variables be pushed to the stack as pointed to? Yes. Or can you do raw variables on the stack with variables? There's a plenty amount of ways to just push a raw value on the stack without variables. We don't need another one, I think. Variables are kind of a very specific mechanism for a very specific thing. Let bindings push the raw value immediately. Constants push the raw value immediately. If you need like a raw immediate value, use one of those mechanisms. Variables are like about a different thing. They're completely about different things. They are about having a place in the memory that you can refer to. If you need to have static memory, you can just use malloc proc in Porth to have the same effect. If you need static memory, you can just use malloc. I'm not sure if I understand you, I'm sorry. Anyway, so let me actually commit whatever we have. So what should I say in the commit message? I think I know. Introduce at intrinsic. So, and what's interesting is that at is a standard word in Porth. It is a standard word in Porth, right? So what it does, it just takes the pointer on the data stack and dereferences that pointer. It reads from that pointer. But in Porth, it is actually untyped. The whole language is actually like very weakly and dynamically typed. But here we have like a statically typed version of that. And at some point when the type system is well developed, some of this code may look like a Porth code, but it's semantically not going to be a Porth code. It's going to be like a very well type checked. Yeah, so that's the goal essentially, right? Just get rid of things like at 864, at int, at pointer, and replace all of that with at without sacrificing the static typing, right? Just like get rid of all of these things and just replace it with this single word, but at the same time, the type system should still work as it is right now. So that's the goal, essentially. That's the goal. Okay. Oh boy, so I don't feel like we'll have enough time to actually introduce variables, so I think I'm gonna introduce variables off screen, right? But I already explained how the variables are gonna work, right? Essentially, you would just like define a name, right? Var x, and then you would provide types in there. And the reason why var is a block is because the description of the type may get quite lengthy, right? Because maybe you want to have, maybe you want to store a pointer to an integer. And what's interesting is that when you push such variable, you would push actually a pointer to a pointer, right? So like so. And in the future, when we're gonna have more like types and more different type constructors, this entire thing may become more and more lengthy, right? So we'll have more things in here that describe the memory layout of this entire thing, right? So we're gonna have like a separate small mini language like of types that describes the memory layout of particular variable or something like that. So that's gonna be the idea. All right, so any other on-topic questions? I didn't really see any on-topic questions anymore. All right. Okay, I guess that's it for today, so people don't really ask anything on topic. So that's it for today. Thanks everyone who's watching me right now. I really appreciate it. Thank you for all of the subscriptions, for all of the beats and stuff like that. I really appreciate the support. Thank you. And yeah, I gotta go. So off screen, I'm gonna just introduce the mechanisms of variables. It's not gonna like anything new, right? So I already basically described how it's gonna work. And I probably also implement something like store, right? So, and store is gonna work like fetch, right? But it's just like allow you to do this kind of stuff. So, and yeah, and we're gonna move with the type system in that direction from now on, right? So we're gonna make like the type system more and more powerful. We're probably gonna introduce structures, right? So that way you would be able to define a variable of a particular structure, like a string, right? And then when you push like X, you would have the type of string pointer 2. And then you would have operations that take string pointer 2 and turn it into something like integer pointer 2. And that is going to be something like count, right? Like so. And that way you would be able to access the size of the string. So, and another one could be something like a data, which accepts the string pointer 2 and returns actually pointer 2, right? So and that way you can access the bytes of the string, right? So you would have like these different accessors that take specific pointers and turn them into different pointers of different types, allowing you to like offset and find specific fields within the structures. And these kind of things are going to be generated, of course, automatically. You only would describe the structure, and then it will give you all of these accessors that work on specific pointers and stuff like that. That's at least the idea. I'm not sure how it's going to go, but as you can see, we're already pushing the code base towards that specific direction. Right, so I'm trying to slowly trying to make Porth a better language, a more enjoyable language. So yeah, that's it for today. Thanks everyone for watching, and I see you all on the next recreation programming session. Love you.